So let's continue our lecture on alcohols and phenol. So in this part, in this lecture, let's discuss what are the common reactions of alcohols. So we can divide broadly the reactions of alcohols into two types. Number one is substitution reactions. And number two is oxidation reactions. So these are the two main classes. Under substitution reactions, we'll see two types. One is SN1 reaction and SN2 reaction. So nucleophilic substitution 1 and nucleophilic substitution 2. So you already had introduction to this, but we'll try to focus on the reactions specific to alcohols. Now, let's start with SN1 reaction. So SN1 reaction for alcohols, SN1 only occurs for tertiary alcohols. So when you don't have any hydrogens on the carbon, alpha carbon, so that alcohols are the only ones that undergo SN1 reaction. So when you use SN1 reaction to convert tertiary alcohols, they convert to alkyl halides using HX. Any compound that involves HX, for example, any halic acid, HX. So where X can be X can be chlorine, bromine or iodine. So these are the main cases where you would get an alkyl halide. For primary and secondary alcohols, the reaction generally occurs under SN2 mechanism. If you remember, SN1 mechanism involves 1 here. So the 1 represents that the rate limiting step is only one step. So there's only one step that limits the rate of the reaction. In SN2, there are two steps that limit the rate of the reaction. And let's look at it separately. So what happens in a SN1 reaction? So let's take an example of a tertiary alcohol. So let's say we have a tertiary alcohol here. Now, under reaction with any HX, for example, let's take hydrogen bromide. So where the bromine contains 6 lone pairs and the oxygen contains 2 lone pairs. Now what happens here is the oxygen, being a little more of a atom that's much more electronegative, will try to attack the proton on the bromine. So these 2 electrons will go to the bromine. So you'll be left with an atom that's with a positive charge. So what this does is it creates a carbocation intermediate. Now this carbocation intermediate, so the bromine that's going from here, so the bromine that leaves has 8 electrons and is negatively charged. So this bromine will then use a nucleophilic attack and attack the positive charge, and finally creates the final product where you have with bromine. So notice that the reaction in total converts an alcohol with an OH group into an alkyl halide with bromine. So this is the final reaction. So there are two things that are happening here. First mechanism is the proton attack, and the second mechanism is the nucleophilic attack. So let's not call it proton attack, let's call it proton transfer. So what happens to the proton here? So the oxygen has 2 lone pair of electrons. So what happens here is that it creates a water molecule. So it basically leaves. So the OH group is turned into a water molecule to facilitate it to leave. Why do we need to do this? is because OH is not a good leaving group. So it does not leave easily. So we have to convert it to something else for it to be moving from that particular place. So notice that there is an intermediate step in the reaction. That's the reason why this is a SN1 reaction. Notice that SN1 reactions have an intermediate step. So there is an intermediate that's formed. So that's why it's called SN1 reactions. So this is the total SN1 reaction in presence of HBr. So it also reduces H2. So this is the first reaction that we generally see here. So that's the reaction you see here. Next, let's look at SN2 reactions where we have a primary alcohol. The problem with using SN2 reactions for a primary alcohol, you know that we have to have proton transfer again. So the reaction will happen similar to this, but the difference here only persists on the side. So it looks exactly similar. You have HBr. So the OH, the oxygen undergoes proton transfer. So what happens here is that this molecule, the oxygen, takes two hydrogens with a single lone pair of electrons. So what this does is it wants its electrons. So it takes the electrons from the molecule and it undergoes a leaving group. So when the next step, you lose minus H2O. So you'll be left with bromine getting attached to the system. So you have proton transfer in the first step. In the second step, you have the loss of leaving group and a nucleophilic attack. Remember that in the last step, when you notice that it did not happen simultaneously, the loss of leaving group happened separately and formed an intermediate and then undergo a nucleophilic attack. But here, both of them occurred simultaneously. So both of them occur simultaneously. So this is the reason why it's a SN2 reaction. So if a reaction occurs where there is no intermediate formation, we call it an SN2 reaction. So this is the common reactions that we saw. So these are the two substitution reactions that you generally see. Now, that's for bromides. How do you create an alkyl chloride? So to create an alkyl chloride, we use zinc chloride and we use it with HCl. So we have an alcohol that undergoes a reaction with HCl and zinc chloride to form alkyl chloride. So alcohol becomes an alkyl chloride using HCl and zinc chloride. Now, why is it that we need the zinc chloride? Is because notice that I already told you is that OH itself is a bad leaving group. So what happens here is that the zinc cation is basically making the OH group a better leaving group. So what happens here? The oxygen attacks the zinc ion and attaches itself to zinc chloride. So now what happens? It's easy for it to remove, to making it an easier compound, and then the chlorine attacks it to create a SN2 reaction. So this again, the exact same reaction. The only difference between the last reaction and here is the ZnCl2. The ZnCl2 converts OH into a better leaving group. So by itself, it never leaves. So we generally have to use some other compound to make sure that it can leave. Next, so the other way of removing the OH group, so OH group can be converted into good leaving group, is by using what we call tosylate chloride. So tosylate chloride is called TSCl. So TSCl in presence of pyridine. The same thing in place of OH, what we generally do is we replace OH with OTS to make a bad leaving group into a good leaving group and then undergoes a SN2 reaction. So the tosylate here can undergo SN2 reaction to obtain an alkyl halide. Now, one main part to remember is that the conformation actually changes from R to S. So when you change the structure, for example, here we use tosylate chloride, but we use no sodium bromide here. So the bromide is the anion. So in place of OH, you get Br, but the R becomes S. That's the main purpose of an SN2 reaction. So SN2 changes the conformation of the chiral center. So changes the conformation of the chiral center. Next, we have primary and secondary alcohols. We can also convert them into alkyl halides, but by using sulfate chloride, sulfoxychloride, and put phosphorus bromide. So sulfoxychloride, SOCl2 and pyridine, we can use the same reaction occurs here as well. The first thing that happens is that it makes OH into a good leaving group and then attaches itself by undergoing nucleophilic attack. And PBr3, the same mission to undergo bromination. So this process is called chlorination. This process is called bromination of alkyl halides. What happens in SOCl2 here? What we are doing here is that the OH group again converts itself from a bad leaving group to a good leaving group. And what happens here then is that it forms an intermediate compound. That intermediate compound undergoes rearrangement and finally makes it into a good leaving group where the chlorine can come and attack it to form the final compound, which is alkyl chloride. So we have propanol converting to propyl chloride. So you have propanol converted into propyl chloride. The byproduct is important here. So the byproduct when you react with SOCl2 is SO2, sulfur dioxide, and a chlorine radical. So the chlorine ion, chloride ion. This chloride ion can facilitate other nucleophilic reactions, causing it to undergo further mechanism. The same thing with PBr3 as well. So it converts a bad leaving group into a good leaving group, and then the bromine attacks it, undergoing SN2 reaction to form the alkyl bromide. The byproduct that you get is HOPBr2, so basically converting it into another substance. Next, let's talk about another form of reactions that can happen, that is elimination reactions. So we talked about substitution, so I forgot to mention that the second type of a reaction that can occur is elimination reactions. So there are two types of elimination reactions we call them E1 and E2 reactions. We'll talk about it further, but in general, whenever you have a tertiary alcohol that reacts with concentrated H2SO4, it forms an alkene and releases water. A tertiary alcohol uses an SN1 mechanism under these conditions. Here, it also does the same process, but the difference here is that there is no substitution, but there is elimination. So let's look at the process and how it works. So for example, let's say I have a tertiary alcohol. So let's say it it comes into contact with an acidic medium. Acids contain H3O+. So H3O+ is basically oxygen that's attached to 3 different hydrogens with a positive charge. So now what happens here is that the oxygen here undergoes proton transfer, where the oxygen attacks the proton from H3O+. So what happens now is that this compound then creates oxygen with 2 hydrogens. Right? Now we have only 2 electrons on the oxygen. Now 2 electrons, so because it's losing electrons, so it creates a positive charge. Now what happens here is that this compound in itself cannot stay on its own. So what it will do is it will attract its own electrons towards oxygen, creating a carbocation intermediate. So what it does is it creates a carbocation intermediate. It leaves and creates carbocation intermediate. Now in place of the carbocation intermediate, what's going to happen? So understand that these are carbons. So this is 1, 2, 3 and 4 carbons. Each carbon will have its own hydrogen. So what happens here is that this hydrogen, because it's really close to the positive charge, it donates its electrons to the bond and flees out. So it goes out to create H plus. So now remember this part. When it goes, what does it do? It creates a negative charge here with 2 electrons on this end and a positive charge here. The 2 electrons will go on to form a bond, finally creating the alkene structure. So this is how the SN1 mechanism works here to form an alkene. Now this reaction only happens because the H plus, why does this H plus leave? So that's the first question that you have in your mind. The reason there is H plus is because notice that we talked about H2O that was given out here. Notice that here, once the hydrogen is gone, we are left with H2O. But because this H2O is an acidic medium, it's always ready to take up protons. So the H2O that was there will come right here and attract the proton to form H3O plus, and again creates the differential charge and causing it to finally form an alkene. Now the question is, where will the double bond form? Remember that even elimination always favors the more substituted alkene. What does that mean? It always forms the bond, so it always tries to make a double bond where there are more, where it is connected to more number of carbons. For example, if you take this compound and write down where will the bond form. So the OH leaves. So the alpha carbon is this carbon. So this is the alpha carbon. The only way it can form a bond is either it can form a bond with this carbon or it can bond with this carbon. Now, which will it form with? Here, the carbon here is bonded to hydrogen. This carbon is actually bonded to another carbon. So this becomes a less substituted carbon. This becomes a more substituted carbon. Provided both of them will form, both major and minor product will form. But it will be the major product will always be the more substituted carbon. The minor product will be the less substituted carbon. Only when you get a less substituted alkene, the only case where you get that in E2 is in E2 elimination by using a strong and bulky base. So let's talk about that. If you have an alcohol if you convert the alcohol into a better leaving group, so then you need a strong base that can promote E2 reactions. So for example, in this, it's the same alcohol. If you convert the OH into some other group, for example, say tosylate chloride, now by using a base such as sodium ethoxide, what you can do now is convert this into two products. In general, whenever elimination occurs, there are two general products formed. One is called as a Associative product. So Associative product is the more substituted alkene, and the other is the Hoffman product, which is the less substituted alkene. Notice that the ethoxide ion formed here has less number of carbons, so this is a strong base. For example, if let's say you have butoxide, for example BuOK, so terbityl potassium terbutaoxide. This is a bulky base. For example, this is a bulky base which is generally going to be weak. So Hoffman product is formed when you have a weak base. Zaitsev product is formed when you have a strong base. So which means that a simple base forms the strong base, which forms the Zaitsev product. A bulky base forms the Hoffman product. So the more bulkier the base, the more the least substituted the compound. E2 reactions are generally preferred over even reactions. The reason mainly is because E2 pathway is not susceptible to rearrangements and regional selectivity, and because you can control it. Even reactions cannot be controlled, so that's why it's preferred to have E2 reactions. Now let's talk about the next reactions, oxidation. If you remember, when we talked about the preparation of alcohols, we talked about how to form by reduction of a carbonyl compound. But what happens is oxidation is the reverse of reduction. So oxidation is the reverse of reduction. So what is happening here? When oxidized, an alcohol under oxidation forms carbonyl compounds. A carbonyl compound under reduction forms alcohol, but an alcohol under oxidation forms a carbonyl compound. So under reduction forms the alcohol, under oxidation forms the carbonyl compound. Now, when you oxidize primary alcohols, you get an aldehyde. So remember this, primary alcohols, you get an aldehyde. But aldehydes are not stable, so then convert into carboxylic acid. Secondary alcohols convert into ketones. That's it. There is no choice that they cannot convert into further compounds, so that's the final compound that they get. But when you do tertiary alcohols, there is no reaction. So because tertiary alcohols do not undergo oxidation. Because the main reason for they do not undergo oxidation is because they do not have any protons. Unless they have a proton, the carbon has a proton, they cannot, but notice that this proton is not connected to the carbon. So oxidation only happens to the carbon, not for the oxygen that's attached. So remember that position. So at alpha position there is no proton, so that's why they cannot undergo any oxidation. Now let's take an example. Let's say I have some alcohol. So let's say we have an alcohol here. So let's say it undergoes oxidation. So the first thing to remember, we have to determine whether this alcohol is a primary or a secondary alcohol. So the carbon is connected to one more carbon. That's it. So there is only one carbon that it's connected to. So it only has one R group. So which means that this is a primary alcohol. So I already told you the primary alcohols undergo aldehyde formation. So what happens here is this alcohol basically creates a double bonded oxygen. That's it. This is your final compound. And under further oxidation, what happens here? This alcohol basically creates a double bonded oxygen plus NOH. So this is the final part, which is the carboxylic acid. Right, so this is the aldehyde. So then forms the carboxylic acid. So when you do a secondary alcohol, it forms ketone and stops right there. So as general secondary alcohol, if you take an OH group with an OH group with two side chains, what happens here is that in place of the OH, you lose one hydrogen and you get a double bonded oxygen. So this is the final part. Now, what are the common, how do you do oxidation? We have a large number of oxidizing agents that can be used to oxidize an alcohol, but the most common oxidizing agent is what we call chromic acid. Chromic acid can be formed from either chromate, chromium trioxide, or sodium chromate in an aqueous acid. So chromic acid is this compound with chromine in the center and two double bonded oxygens on each side with OH groups attached to it. Two OH groups attached to it. The other name for chromic acid is also called Jones reagent. So Jones reagent is basically an oxidizing agent. So now what happens here when you take it through an alcohol system? So what happens here, let me write it down separately. Let's say we have a general secondary alcohol. So let's say it reacts with chromic acid. Now what happens here is that this chromic acid undergoes a chromate ester formation. So what happens here basically is that these two hydrogens will combine and to form hydrogen and leave. So this H and OH combine together to form H2O and they leave. So the final product that you get this is called as the chromate ester formation. It's called as a chromate ester. Now once it forms the chromate ester, notice that I already told you that there is a water molecule that leaves. So there is a water molecule. Now this chromate ester, this water molecule will not stay on its own. So what it will do? So it basically take up this chromate ester So this chromate ester. So uses the water molecule that's released there, uses the water molecule here. So what happens here is, because it's an acidic medium, the water molecule wants to form H3O+. So what this does is that this oxygen will attack the proton on the alpha carbon, because notice that there is no other proton left on the entire carbon. So only on the alpha carbon there's only one proton, it's going to attack that proton. Now once the proton leaves, so the proton will go out, so giving it H+, but these two electrons are there, so these two electrons will come back to the compound. So these two electrons will stay here, so will come back here, and the oxygen, noticing that there are too many electrons, will take its electrons and basically donate it back to chromium. So notice that it has two bonds to form, so it creates a structure. So now combining all these three arrows, what do you get as a final compound? You have oxygen with R and R. So notice that this is a ketone. This is how you get your final product. So this is your final product for the reaction, and you end up with H3O plus and hydrogen chromium trioxide. So this is the final product where you end up with a ketone. So this is an E2 reaction or elimination 2 reaction where there is going to be a rearrangement. Now this chromic acid can also oxidize primary alcohols, but finally it will form a carboxylic acid. So when you do the same reaction, the primary alcohol will undergo an aldehyde and then form the final carboxylic acid. But if you want to stop it to form an aldehyde, what you can do is we use a compound called pyridinium chlorochromate. So which is a P, with the other name for it is called PCC, the oxidant that's used to produce aldehyde. So in this reaction, it does not undergo further reduction to form the carboxylic acid, but it stops right here. But if you use chromic acid, it continues further to form carboxylic acid because there is no stopping point. But you can control and form an aldehyde using a primary alcohol. Again, remember that the alcohol you need for an aldehyde is always going to be a primary alcohol. This is the compound pyridium chlorochromate, which is basically chromium trioxide with a chlorine and a pyridine molecule. Now, if you want to have a secondary alcohol, so the secondary alcohol to convert into a ketone, the two ways that you can do it, you can use chromic acid or PCC and convert it into, so you can use chromic acid or PCC to convert it into a ketone. But again, tertiary alcohols will never undergo this, so there is no way you can have a tertiary alcohol forming the final product. So chromium reagents in general are generally toxic and really horrible for the environment because they are toxic metals, and once in the water they can dissolve easily and they can cause a lot of chaos. So alternatives generally that have been developed are, the first one is called Swan oxidation. Swan oxidation uses a reagent called dimethyl sulfoxide and oxalyl chloride to form an active oxidant. So this is DMSO with dimethyl sulfoxide, and you have oxalyl chloride. So oxalyl chloride is basically two carbons with two chlorines on each side and two oxygens on each side. This also creates the same effect as that of the original compound, so there's not much difference here. Next, so Swan oxidation also converts primary alcohol into aldehydes and does not undergo the same the problem with chromic acid, where it converts it into a carboxylic acid. So the activity only occurs until it forms an aldehyde. The second alternative that was developed is called Des-Martin pyridine oxidation. So which is it basically yields an analogous results as that of the Swan oxidation. Again, a primary alcohol will convert it into an aldehyde. A secondary alcohol will convert it into a ketone. Now, so take this example and try this now, and try to tell me whether you understand how the process works, and try to do this reaction. Understand that, remember that we are using chromium trioxide. So chromium trioxide H2CrO3 basically means that we have to use the reaction has to predict, basically undergo oxidation And remember that if it's a primary carbon, if it's a primary alcohol, it becomes an aldehyde. If it's a secondary alcohol, it creates a ketone. And because it's a H2CO3, the aldehyde will basically end up forming carboxylic acid. And remember that this also is there. So notice the second part. So to give you a hint, look at this part. So this is the aldehyde. So this aldehyde will convert into a carboxylic acid. This OH group here has two parts, so left and right. Here it's a secondary alcohol, so the secondary alcohol should convert it into a ketone. Now the last one is OH. This is a primary alcohol. It should convert it into, so this is a primary alcohol. It basically should convert it into an aldehyde. So, and then finally it should convert it into, so the carbon here should convert into a carboxylic acid. So try this now and try to predict what would be the final answer. I have given the answer here, so you can use this as your final answer. Check whether your answer is correct or not. So right here, notice that the final product, if you have primary alcohol, converts into carboxylic acid. So the aldehyde also will convert into a carboxylic acid, and the secondary alcohol will convert into a ketone. So let's discuss the next topic, biological redox reaction. So we know that we talked about both oxidation and reduction. So now we want to talk about how biological organisms use redox reactions to convert from alcohol to carbonyl, carbonyl to alcohol. So nature employs these mechanisms very efficiently. The reason they are used is because they are generally complex and specifically because they are selective. So one of those such reducting compounds is NADH. So NADH, nicotinamide using agents, where you have a sugar, a base, an adenine base with a diphosphate linkage, and another sugar connected to a reactive center. The reactive center is what reacts in the reaction. Either it undergoes oxidation or reduction. So this is the part that undergoes the oxidation or reduction. Where do we see this? One of the most reaction sites in the reaction is the hydrogen on the compound. This hydrogen undergoes oxidation, so it oxidizes compounds, it oxidizes ketones, and uses acid using enzymatic catalysis to form NAD+. So if we focus on this, NADH forms NAD+. The reason this is important is because conversion from NADH to NAD+ releases energy. This is the energy that forms ATP. So one of the common places where you would see this is by production of alcohol. So NADH with ketone process creates alcohol and a base. So where will you see this of converting carbonyls? One of the two places where you might see this is in the citric acid cycle and the electron transport chain. So where you convert from ADP to ATP. So when you use the citric acid cycle is the main place where you convert NAD plus into NADH, and using the compound that is released there, you use the energy, and in reverse, when you use the energy, what you do here is by conversion from NADH to NAD plus, it releases energy. That energy release creates ADP to ATP. So this conversion of NADH to NAD plus is one of the most important biological processes that you will encounter, and you will see this process occurring in a lot of biological reactions, because this is the source of energy, is one of the sources of energy in the citric acid cycle to create ATP, to create ATP. So one of the most key roles, so it plays a key role in the metabolism. We will discuss a lot more of it at the end of organic chemistry when we discuss metabolic processes. During the citric acid cycle, we will discuss a lot more about this. One of the most common processes of conversion from NADH to NAD plus is in the metabolism of lipids. And also you might see this in the citric acid cycle, where you metabolize sugars. Next, remember that tertiary alcohols do not undergo oxidation because they lack an alpha proton. But you might also expect the same thing with phenol. Notice that a phenol generally should not have any alpha protons at the alpha carbon. The reason mainly is because there is only one hydrogen on each of these sites. So because the hydrogen is replaced by an OH, we generally think that it might have the same, it does not react at all. But the plus point that this phenol has over the tertiary alcohol is because of its resonance. Resonance makes it more readily oxidized than any other primary or secondary alcohols. One of the reasons why it can do that is because the electrons are always on the move because of resonance. Because electrons are destabilized, they are always on the move, and that motion causes it to react easily and to get oxidized faster. Now, phenol in general oxidizes to form a compound called benzoquinone. Benzoquinone is basically a ketone with two oxygen groups on opposite sides of the carbons. So this is called as, the compound is called as benzoquinone. So quinone comes from the word two oxygens, diketone. So that's the other name that we generally see. Under reduction creates hydroquinone. Hydroquinone is where you get OH groups. Under oxidation we see benzoquinone. So where you see two oxygens. So quinones are converted into hydroquinones, which is one of the key processes in the process of cellular respiration. So cells can respirate or remove oxygen or add oxygen by this particular process. This is one of the processes that can use this. Now, the other compounds that act as well are called ubiquinones. Ubiquinones act to catalyze the conversion of oxygen into water, and they are generally found in all cells in nature. So this ubiquinones contain about 6 to 10 carbon long chain compounds with a benzoquinone on the side. So ubiquinones use protons that they get from NADH and create NAD plus to create hydroquinones, and then in the second step they use that and oxidize to form ubiquinone back again. So by this way, the final product, what it does is it's using protons and oxygen and converting them into water. So this is the process by which water is created out of hydrogen and oxygen in your body. So this catalysis is called ubiquinone catalysis. Next, let's talk about synthesis strategies. So we already discussed that the reactions that fall under the first group, so where you change the carbon skeleton, there are two ways you can change the reactions. One is to change the carbon skeleton, if you recall from organic 1, or the one other way you can do this is by changing a functional group. So when you want to change this carbon skeleton, you generally do by changing whether a triple bond to a double bond to a single bond. If you want to use a Poisson catalyst or a Lindlar's catalyst, you can convert from a triple bond to a double bond. And if you want to reverse that, we can use excess sodium amide. And if you want to convert from double reaction to a single reaction, we can use catalytic reduction, catalytic hydrogenation. If you want to reverse that, we can use bromination. So that can elimination reaction, which involves sodium methoxide. Now, we have seen the reactions that can convert primary alcohols and into aldehydes and secondary alcohols into ketones. So when we use an alcohol with PCC, we can convert it into an aldehyde. Or if you want to reverse it, the reduction process involves lithium aluminum hydride. And if you want to convert secondary alcohol into a ketone, we can use sodium chromate. So, and if you want to reverse that, we use lithium aluminum hydride. Now, these are the main things. If you want to convert alkynes into alkenes, we have to do reduction. The same thing happens with ketones as well. When you want ketones to become alcohols, we use reduction, and alkyl halides to become alkanes, we use reduction again. So in the forward direction we have reduction, in the reverse direction we have oxidation. So these are the 6 functional groups that can be grouped by oxidation state. So I have put the entire reactions or the common synthesis strategies in one single page, so you can go through them and look over all the reactions. So, and use this as a simple step, because recall the Grignard reaction. So notice that CH3 is the one that gets added and converts it into an OH group. The CH3 has a lot of uses because excess CH3 can make it into a long chain compound. So you're basically converting the carbon skeleton. So you can change the carbon skeleton by the Grignard reagent. So we can use Grignard reagent to change the carbon skeleton. So with that, we end the chapter on alcohols and phenols. So I'll see you again in the next lecture.